Yeah, if you have it, turn it in. I don't, but there's no. That's right. As long as you keep it together. Yeah, that's fine. Yeah, I can usually keep it all together. Anybody else? This right here is fine. Thank you. Thanks.
Don't bother me.
Bothers me more. Anybody else? Bonus question? Thank you. Anyone else? Okay. All right. So I'm going to do like a breakdown of the grades and take a look at the whole class. When we start class next time, I'll talk about the grades, and we have a final exam. Not next week, but the week after, right? So I handed out a review last time. Did anybody not get that? Need a review? I just posted all the videos yesterday. Last week I left my camera at work when they closed campus last Thursday real quick, and I just kind of left and forgot my camera. So I uploaded all the videos yesterday, so everything should be up to date. Except for the video where I showed the grades. Remember that? Remember that? Yeah, I cut that out, so there's 5 minutes missing, just so you know. All right? Okay, we are going to do a little bit more. I'm going to do one more optimization problem, and then we're going to move on because we're behind. So I want to try and get through some more material. We have, what, 4 class meetings? All right, so I'm going to show you kind of a classic optimization problem. Remember the related rates where we were doing like a balloon is being inflated at a certain rate? Remember those problems? You didn't like those very much. The classic problem there is the ladder sliding down the wall. This is kind of the classic problem when it comes to optimization. Let me just go ahead and put this up here. Let's say you have a sphere of radius. All right, now we need to make a decision here. Do we want this sphere to have a fixed radius like 1 foot or something like that, or do we want to do it arbitrarily, like for radius of r? If we do radius r, it's going to be harder, but it's kind of up to you. Do you want to do arbitrary r, or just let's use a number?
Are we going to be required to know how to do it?
Well, I probably wouldn't give you something with r on it. Let's just fix it at how about 4 feet? Okay, that's a big sphere, right? You have this big sphere, 4 foot radius. And what we want to do is find the dimensions and the volume of the largest cylinder which can be inscribed into the sphere. There we go. Anybody else turning in extra credit? Anyone else came in? No? Extra credit from the end of last class? I gave a problem at the end? No? Okay, so let's try and understand the problem first, right? We have a sphere, has a radius of 4. So to draw a sphere, draw a circle, and then you can draw kind of like an ellipse through it like that. There's your sphere. It has a fixed radius of 4 feet. And what we want to do is inscribe a cylinder into this. Now when I say inscribe, you have to understand what this means. It means that this cylinder is going to touch the actual surface of the sphere, but it's going to be inside of it. So imagine a cylinder that looks something like this. Inside of that sphere. Do y'all see it? Now, there are an infinite number of ways I can do this. Let me draw a couple of scenarios. I could have a cylinder that's really, really narrow, just barely touches at the top, comes down like that, right? That would be a very tall cylinder, but it wouldn't be very wide. I could also do something like this. Where we have the cylinders really, really wide, but not as tall, right? And pretty much everything in between. Can you all imagine those different scenarios? Yes? And so what we're trying to do is figure out what the dimensions and the actual volume of the largest possible cylinder that we can get in there. When I say largest, we want it to have the most volume possible. So how can I fill the space of the sphere with the largest cylinder? Okay? Believe it or not, this is used a lot in optimization of like packing things. When they pack containers that they're going to ship overseas, right? You get one shot to put everything as much as you can into these things. They use optimization in how they pack things, right? So, all right. Understand the basic idea? Okay, now in terms of steps, we didn't really have steps, but we had kind of a template of how we approach these. The first thing was to try and get the objective, right? The objective equation or objective function. So what is it that we are trying to do here? What's the objective here? What are we trying to find the maximum or minimum of? Maximum volume, right? We want the maximum volume, right, of the cylinder. Right? That's what we want. The maximum volume of the cylinder. Now look at the blue cylinder here. What is the volume of any cylinder? We need a formula for that, right? So this is in our reference sheets. If somebody gives me a cylinder, right, and I want to know the volume, I need to know the radius of this cylinder. So I'm going to call the radius of this cylinder r, and it's not 4, right? It's not 4. 4 is the radius of the sphere. And we've already seen that our cylinder can be different dimensions, so that radius is actually a variable right now. So the volume is pi r squared times the height. You also need to know the height of the cylinder to determine the volume, right? So I want to make this as big as possible. I'm just getting that from the formula off the sheets. I want that to be as big as possible, right? So I want to find the maximum, right, of v equals pi times the radius squared times the height. So right now, as you look at it, the volume depends on two different things, right? In order to determine the volume of that cylinder, I need to know r, which is a variable, and I need to know h. Those are going to change, right? The taller the cylinder is, the more narrow it is. The wider it is, the shorter it is. So these are two variables, and in order to do any calculus that we've learned, we need to have one variable, not two. So now comes into play what? What part? The constraint, right? There's something that is constraining what my r and my h can be. They can't just be anything, right? So my constraint can y'all think of any constraint I have? The radius of the sphere is constraining the cylinder, isn't it? I mean, the sphere is fixed, right? So how does that control things? It's kind of hard to see this, but the radius right? The radius of the sphere is equal to 4. That's a constraint, but how is that going to allow me to get this to one variable? So I don't know if you remember last week, but what we were trying to do was in the constraint, we were trying to come up with an equation that had both of these variables in it. And then we would solve for one of them and then plug that in over here. So we need to somehow, using the constraint of the sphere has a fixed radius of 4, we need to use that to come up with an equation with r and h in it, right? Okay, so this is the hard part, all right? So I'm going to show it to you because it's the first time you're seeing something like this. I'm going to do something, I believe we did this in the past, maybe not. I'm going to imagine taking this sphere and this cylinder is inside of it. It's arbitrary, right? And I'm just like, this is one way I could draw it. Imagine I just slice through the center of the sphere, all right? Slice through it with a big old knife or something, right? Cut through it and then open it up. And let's just look at what we call a cross section of it, right? So we're just looking at half. If I look at that, what do you see? What is it? It's no longer three-dimensional, right? You're looking onto it. It would be a what? A circle, and inside of it would be a rectangle, right? Let's take a look at that. If I draw a circle, that's my sphere. And then I draw my rectangle, which is my cylinder. Right? And then let's put a point here in the middle that represents the center. I'm trying to come up with a relationship, right, between R and H over here. Somewhere in here I need R and H to be connected. And somehow the 4 is going to come into play. So do you all see this? Do you all agree that, let me see, I'm running out of colors here. Do you all agree that the distance from here to here, that would be R? Right? That would be R. And do you agree that the distance from here to here, well, you tell me, what would that be? Half of H, right? This is all of H, right? This would be half of H. Now you might be saying, well, what in the hell are you doing, right? I'm about to make a triangle. Do y'all see where my hypotenuse is? Hypotenuse goes from the center to that corner, and do you know that side? What is it? It's the radius of the sphere, right? Because this point goes from the center to the edge of the circle, to the edge of the circle is the same as the edge of the sphere. So that's 4. Does everyone see that? That's not a very natural thing to do, is it? To like cut it, open it up, take a look, right? But now you see it. Who has a question? Yes? Okay, so remember, the cylinder in here, right, has a height of H, yes? And when I cut this in half and we're looking at it, this is H from here to here, right? So if that's the center of the sphere, that's also the center of the circle, which is the halfway point between here and here. So that's half of H, right? Any other questions? Do y'all see what I'm going to do with that triangle? It's a right triangle, isn't it? And I have Pythagorean, don't I? I have that r squared plus this squared equals that squared. And that is an equation that has r and h in it. And then I can use that and solve and go put it in over there. It's kind of clever, yes. Not very natural, but clever. And I'm not claiming it's, someone showed me this the first time, right? So it's not something that people naturally stumble upon. Okay, so look, from that, I know that r squared plus 1/2 h, that quantity squared, must be 4 squared. And that is an equation with both r and h. Be careful on that 1/2 h squared, because when you square that, you have to square both the 1/2 and the h. Right? You square 1/2, 1/2 times 1/2 is 1/4, h times h is h squared. Now, you have a decision to make. Do you want to solve this for r, or do you want to solve this for h? Because whatever you do, you got to plug back in over there. So it seems natural to want to go for h because h is right here, right? You can just solve that for h. But don't we also have r squared? See, if we solve for h right here, do you agree that we will have to take a square root at some point? And then I'll have plus or minus, and that'll be a mess, won't it? But because my formula over here has r squared in it, and this also has r squared in it, wouldn't it be easier just to solve for r squared and then just plug that in over there? We could do it either way. It'll work both ways, but I think solving for r squared is probably the more efficient way here. So I'm going to solve for r squared by subtracting 1/4 h squared on both sides. And then I'm going to take that answer and plug it in over here, and then my volume now becomes pi, okay, r squared, which is this, 16 minus 1/4 h squared times h. So pi, that's r squared, right? R squared is this. So no, I'm not squaring it, right? Because it's already squared in the formula, right? And then times h. Any questions? No? Sure, sure. Is the volume now dependent on one variable alone? Yes, right? Just depends on h. So you give me h, I give you the volume of the cylinder. So now I can look at the volume as a function of a single variable h. So I'm just changing the notation to let everyone know I've got it to a function of single variable. Then I have pi. And then what I'm going to do is I'm going to go ahead and just distribute the h through here. 16h minus 1/4 h cubed. I could also distribute the pi through. Right? I could pass that pi through there. Do y'all want to? We can? Doesn't matter? Yeah? No? Yes? We have to differentiate this, don't we? At some point. And if I leave the pi out here, it's not a product rule, right? Because that's a constant. So it'll just come for the ride when we take a derivative. So I think I'm just going to leave the pi out front. Y'all good or no? Okay. Now, thank you for the nods. The nods help. Yes, we're okay. What now? Important point. Important part of all these problems. What's that? Domain. You got to figure out, are you going to use the closed interval method or are you going to use the open interval method, right? So h is the variable. Go back to this picture here. H is the height of the cylinder. Is there a smallest height that you could have? Smallest. Well, could it be negative? No, okay. Could it be 0? Yeah, you wouldn't have a very good cylinder. You'd have no volume in that cylinder, right? But it would still, that would be one extreme, right? You have your sphere, and then you come in here and say, draw a cylinder that has a height of 0, which would mean it's basically like a disk, which would have no volume. But that would be an absolute extreme. And we could say h could be 0, right? What would the biggest h could be? What's the biggest value it could be? What's that? The height could be all the way from the North Pole to the South Pole, couldn't it? Past that, you're punching through the sphere. So what's the distance from the North Pole to the South Pole? 8, right? Doubling the radius. So we can look at this on a closed interval from 0 to 8, right? From 0 to 8. Hold on real quick. Let me make sure I silence this. Okay. All right. So how do we do closed interval? We do critical numbers, right? We find the critical point. So take the derivative of this function, set it equal to 0, figure out where it's 0, figure out where it doesn't exist. And then with those answers, well, let's do it. And then when we get to it, I'll remind you. Are we going to be doing test points and figuring out where it goes up and down? No, not for this method, right? So I'm going to go take the derivative now. Pi is going to come for the ride, right? It's just going to come for the ride. And now I'm taking derivative of this in here. What's the derivative of 16h? Just 16, okay. And then minus, okay, this 3 power rule, the 3 comes out, right? 3/4. So the 3 over the 4 h to the second power, and we're done, right? We're done. Pretty clean, nothing crazy there. Now I'm going to set this equal to 0. All right, so when I set that equal to 0, it's actually kind of nice that that pi is out there, because I'm just going to divide everything by pi first. And that'll give me 16 minus 3/4 h squared equals 0 still. And the way you solve this is kind of up to you. I'm going to move the negative term to the right-hand side to make it positive. I'm going to multiply both sides by the reciprocal of 3/4, which is 4/3, and that has the effect of killing off the fraction on the right. On the left, I have, what's that? 16 times 4, 48 over 3. Hey, wait a minute, hold on. That's not right. Why did I say 48? It's what? 64?
Yes.
64 over 3 equals h squared. Yes?
Wasn't it h cubed, or we're not looking at that?
Where?
Like,
I took the derivative,
oh, okay.
right? So the 3 comes down, and the power comes down by 1.
Oh.
And then here I took derivative of h. Derivative of h is 1. Yeah, be careful. I'm taking derivative, right? All right, square root on both sides, right? Square root on both sides. So if I take square root, I'm going to have plus or minus the square root of 64/3 equals h. And I'm going to throw away the negative, because having a negative h doesn't make any sense. So h is equal to, I'm going to do the square root of top and bottom. Square root of 64 is 8. Square root of 3 is square root of 3. And then on our calculators, let's get that as a decimal. You having fun? All right. 4.61. So h is approximately 4.62, let's say. Approximately 4.62. And I said last class, decimal's fine. Exact answer is better, but you know, either one, all right? Okay. Now, that's what makes the derivative 0. I also need to check, where does the derivative not exist? Well, this is the derivative, right? This is a polynomial function. It exists everywhere, so I have no issues here. So I only have one critical number, right? One critical number, that's it. What do I do with this? Plug it into the original function along with the two endpoints, right? But we kind of already know what's going to happen at the two endpoints, right? If your height is 0, what's your volume going to be? Okay, and if your height is 8, that means it's just going to be from North Pole to South Pole. You can't have any width then, right? So the volume's going to be 0 as well. But I'll check it just to show. Okay, so my next step, I didn't put here closed interval method. You might want to put here, you know, in your notes, closed interval method, just so you're aware. So now I do the volume at 0, the volume at 8, the volume at 4.62. Here's our volume function. If you plug 0, it's pretty easy to see. 0 here kills it, 0 here kills it. That's all 0. You get 0 out. If you plug in 8, you go 16 times 8. But that's going to be exactly the same as doing 8 cubed divided by 4. These two would subtract, you would get 0 again. Okay? So 0. This one we have to do. This one we have to do. So we're going to go pi 16 times 4.62 minus 1/4 times 4.62 cubed. I'll do that on my calculator. By the way, I'm gonna keep our door locked. Just FYI. If you need to leave, someone's gonna have to let you back in. All right, let me get on my calculator and do this. So I'm getting about 154.7. Anyone else get that? Yeah? Yes? Okay, 154 point, let's go 154.8. About 154.8. Now obviously this is our max, right? Because the other two answers give us zeros. So this is the maximum volume that I can get, right? This is the maximum volume I can get. And do you want to be a different chair or a different seat? Are you sure?
Yeah.
Okay, all right.
Thank you.
So this is the maximum volume that we can get, right? And it happens when H is 4.62, right? Now, just to be precise, what units should this be in? It's a volume, and the radius of the sphere was 4 feet. So anytime you measure volume, it should be whatever unit you have cubed, right? So if you, cubic feet, because of the radius of the sphere was in feet. Okay, so we would say this feet cubed, right? If it was an area, you would say feet squared. If it was a length, you would just say feet. All right, so the largest volume we could possibly get is 154.8 cubic feet. Now that's part of the question. The question said, what are the dimensions and the volume, right, of the largest cylinder? We've found the volume. I need the dimensions. I know what H has to be, right? H has got to be 4.62 feet, but I also need to know the radius of this cylinder. And where would I get the radius from? Not into this one. Go into, remember our constraint? Go back to your constraint. We had this formula. It was r squared equals 16 minus 1/4 h squared. Wasn't that in our constraint equation? Hadn't we solved for r squared, didn't we? And what I'm going to do here now is I'm going to take this and I'm going to solve this for r, because I know what h is, right? So I can say r squared would be equal to 16 minus 1/4 times 4.62 squared. And I'm going to do that on my calculator. 16 minus something's not right. What am I'm missing something here. Oh, square root, sorry. I hadn't taken the square root. I'm like, there's no way that radius can be that big. Okay, r squared is 10.66. Right, the radius can't be 10. All right, so square root of that, 3.26. There we go. Questions? So let's see if our answers make sense. We have a sphere, right? It has a radius of 4 feet. And what we're supposed to do is draw a cylinder in here that has a radius of 3.26 feet. Not quite to the edge, right? So, and then the height is 4.62. So remember, height is both up and down. Total together. So it's really, this is about, if you go like half of this is 2.31, half of that. So that means I go 3.26 out, whatever that is. Then I go up about 2 and down 2 and then draw my cylinder in here, and that will be the biggest volume I can get, right? If this distance from here to here is 4.62 feet, and my radius here from here to here is 3.26 feet, then I will have the largest possible cylinder in there with a volume of 154.8 cubic feet. All right, we're done. Any questions? Every one of these problems is different, right? I mean, last time we were doing farmers with fences, right? Things like that. This is a problem where you don't have farmers and fences, right? You have something completely different, but the same approach, right? You have to draw things, you have to get your objective, right? Then you get some constraint, you get it down to a single variable, and then you do your calculus. So I remember when I was in graduate school, I think I told y'all that in grad school I had to do these things called recitations. Right? I told you, like, I don't know, maybe I didn't. As a graduate student, one of my duties, I got paid by the college to every Friday go in. I was assigned to a certain Calculus 1 class, and on Fridays I'd go in for something called recitation. We don't have recitation here, but what it is y'all know how y'all meet here twice a week? In other universities, like big universities, what they do is instead of y'all meeting for an hour and 40 minutes, you meet for an hour and 15 minutes twice a week, and then on Fridays you go in for another hour and you sit down, and it's basically a big question and answer session. And so you can ask questions about homework problems, things like that, and they throw a graduate student up there in front to answer questions. So I remember as a graduate student, it was terrifying to go into this room of like 100 calculus students, and they could ask you basically any question out of the book, and you'd have to be ready to answer it, right? So when I took Cal 1, I didn't do all the problems in the book, right? So as a graduate student, I had to understand and know what I was, you know what I mean? Like I would get presented with problems I'd never done before. So you have to understand the concept, right? It's not about understanding how to do a specific problem. It's the concept that's important. So I haven't done a ton of examples here, and we don't have time to do more. I hope you get the main idea. The only way to get good at this is to do more and more and more and more practice, all right? So on your review, right, I only have on your, who else needs a review? I don't have many more here. This is the review for the final. On the final exam, I do plan on giving you an optimization problem. On the review, I have a thing here with the fence, right? I have a fence problem here for you to do. But I also assigned some problems out of the book, didn't I? That I wanted you to look at. So to me, that's fair game as well. I mean, I'm not going to pull a problem that you've never been shown or you've never been asked to do yourself. So if I gave you a homework problem and it has to do with finding the maximum volume of a box that doesn't have a lid, that's a problem I gave you for homework, right? If you got that on the final, you're like, what is this? That's because you didn't do your homework, right? So make sure you do those homework problems and that you ask questions if you don't know how to do them, all right? Anything else before I move on?